I managed to, yeah, I think I fixed that. Okay, so as you said, yep, the talk is going to be about polarimetry, and to the lesser extent about how polarimetry can help us to search for the liquid water on exoplanets. And yeah, that's a very difficult task. So some people asked me yesterday what actually is polarimetry, and I thought, well, it's sort of fancy way of putting polarized glasses on the telescope, and I'll show you what kind of glasses there are there for our use. So let's quickly reflect on what Matthew Cole said yesterday, that we're actually living in very interesting times where really, well, within 25 years, we now know about more than 3,000 exoplanets. So problem is now, what kind of planets are they, and are any of them habitable or inhabited, in fact? And as you heard in the previous talks, that question is not really answered, and the characterization of these planets is really quite difficult at this stage. But of course, we had a few surprises on top of this. When we looked at what sort of planets we're finding, most of them actually are in the sizes which don't have equivalents in our own solar system. So they are kind of what we call super Earths, or perhaps mini Neptunes, things like that, which we really don't know anything about. Are they rocky type of Earth? Are they mini Neptunes with the thick atmosphere of hydrogen and helium? Or are they kind of giant versions of moons like we have around Jupiter, made with a thick layer of ice and some sort of water atmosphere? So that's stuff which we have to really try to answer. The other surprise, obviously, which Dan talked about, is that actually when we look at the architectures of these systems, well, it seems like our solar system is really very unique. So, you know, we found also these giant planets in orbits which are very close to the star, and obviously they couldn't be born there. So yeah, that's a different story. Okay, so how we characterize these planets? Well, two of the most successful methods of discovery of these objects can tell us some rudimentary facts about the planets. So radial velocity will tell us something about the masses and modular inclination of the orbit. So if you know inclination, then yes, we get the mass. From transits, we can learn something about the radius of the planet. Both methods give us really orbital parameters, so we learn how far the planet is from the star, and that tells us again something about the temperature which would be on that planet. And if we combine these two methods, we also get from mass and radius the average density of the planet, so we know whether, or we should know whether this is a rocky planet or something totally different. Now, if we want to do something more sophisticated, we try to look at the spectroscopy, and we do the transit spectroscopy, which the sterile light is filtered through the atmosphere of the transiting planet, and at some wavelength light is absorbed and by molecules and atoms in the atmosphere. So that's how we can learn about the composition of the atmosphere, and the dynamics as well, as I've written here, but I'm not going to go through it. Now, there is also another way of looking at the spectra. We can look at actual emission spectra of these planets when the planet is actually almost behind the star. And these can tell us something about the albedo, which is reflectivity of the planet as well. So here these are three sort of examples I would say probably almost the best examples of spectra which we obtained for the planets. This is emission spectrum of the hot Jupiter. Now, what's important to note here, well, there are some absorptions there, which we think they correspond to the water band absorptions. So, okay, there is some water in the atmosphere, but yeah, this is probably gas. I mean, you can't really say that this is liquid water. Then, in fact, in the hot Jupiter, we wouldn't expect liquid water because of the high temperatures there. Now, there is mini Neptune planet here, which when you can look at the spectrum, shows really, high error bars. So these are the points with error bars are data, actual data, which we measure. The continuous line are models, which we provide from the radiative transfer codes. Now, what's interesting to see here is that there are some quite a variety of models which can fit these conditions on these planets, and especially here for this one, which is this one very sort of famous super Earth, which was coined the water planet, where the very sort of featureless spectrum was attributed to the atmosphere being almost entirely water vapor. Now, okay, but that sort of atmosphere can also be formed when there's a lot of clouds on the planet. So again, we don't know much. We don't have a unique way of saying what models are really applicable to these planets. And you can see here that data are pretty sparse still, and with quite a lot of, quite high error bars on it. So, okay, well, let's leave it and go to polarization. How polarization can help to tell us more about these exoplanets. And okay, yesterday I put this slide here just in case someone didn't know what we're talking about. So, well, let's define the polarization. So the linearly polarized light is just an electromagnetic wave that propagates along the preferred single plane. So this is what we see here. In opposition to unpolarized light, where there's no preferred plane of propagating that light. We can also have a circular polarization, which we neglect here conveniently. And so how we produce polarized light? Well, we can use some filters, obviously, and so use polarized glasses. So we put light, pass light through some materials which are birefringent or optically active, and they produce this single sort of plane where for the light, and call it linear. And putting different filters, we can sort of orient it differently and so on. So that's a sort of little basic on stuff on polarization. Now, what processes are actually make light polarized? Well, there are two flavors of processes. The first one is the inherent asymmetry in the actual emission process of the light. So, for example, something like synchrotron radiation, which the light is emitted from spiraling down electrons, and the light is actually almost 75% polarized. The other flavor is just the interaction of electromagnetic wave with matter. So you've got absorption of light. So it's like in this previous example, you put the light through some optically active material, and special directions of polarizations are absorbed. The other ones are let through. And the other way is just the scattering on the molecules of the gas. That gives us preferentially polarized light, depending on the scattering angle of this process. Now, the other way of making light polarized is just a reflection from dielectric, and we probably you're familiar with the glare from water, which is highly polarized, and you use these polarized glasses to actually extinguish the flare. So just cut off that polarized component of light. So these are the ones. These are the processes which polarize light. Now, which processes we actually can detect to characterize the planets through polarimetry? So there are a few. There is Rayleigh scattering, which is the light scattered on gas molecules, and these gas molecules have to be as small as the wavelength of the light we observe, or roughly that's small. And there's also scattering on the bigger molecules, which usually you would find in cloud particles and hazes, and this is described by the Meade theory of scattering, and that it's not as highly polarized as Rayleigh scattering. So in Rayleigh scattering, well, Rayleigh scattering really is something which actually make the sky blue. Yeah? So it has very strong wavelength dependence, so blue light scatters more than the other colors. But that that scattering is highly polarized. So here, if you look at the sky, the full sky, and the sun would be at the twilight or sunset, you'd see that the highest polarization would be actually across the zenith, going across the zenith. So, then you've got the other processes which are really, really cool, because these two processes would actually allow us to detect liquid water in the atmosphere of the planet or just on the surface of the planet. So the first one is the rainbow scattering from the droplets of liquid which is suspended in the cloud. So this is exactly what we see here on the Earth. The rainbow is due to scattering, which is described in the next slide, and that would be actually some evidence that there is liquid water in these atmospheres. Yeah? And again, another possibility is to actually try and detect the specular reflection of the light from the subbody of liquid, like oceans, lakes, and sometimes actually even icy clouds at the top of the atmosphere. So how we go about looking at the polarized emission of the planet? Well, we could just take telescope with a polarimeter, take one image, and that's it. Yeah, and we would sort of see, okay, there is some polarization there. But that wouldn't tell us a lot. So what we really want to know, how this polarization varies as a function of the orbital phase angle. So when we talked about this Rayleigh scattering, and I told you that the polarization was the highest at the 90 degrees scattering angle. Well, so that in the same way you would expect to see the highest polarization at the quadrature of the planet. So you've got light hitting the planet this way, and then the scattered light going to us. Yeah. So that light actually would have the highest polarization, and pretty much we would see something like that if we observe that light in the clear atmosphere. The clouds tend to be less polarized, so if we add clouds, that peak of polarization will sort of be dampened, and when we add more clouds, the situation is worse. Okay, so what can we learn from these scattering processes? First of all, we can find out what is actually the reflectivity of the planet and the planetary radius. So that can be modeled from the peak polarization, and the same, the size and composition of scattering particles we include in that sort of models, and full model will give us all these parameters. The very interesting thing about polarization measurements is that we actually can say something about the inclination of the orbit. And this is something which is quite difficult to do with other methods. So, for example, if we take measurements of orbit, which is of the planet which is in phase on orbit, you'll find that the polarization itself wouldn't actually change across the orbital period, but the position angle of the polarization would be only varied. Now, in the second extreme case, when we look at the edge-on planet, that would produce the highest variations in the polarization across the orbit. So that's pretty funky stuff. Okay, so let's go now and talk about this possibility of learning something about the liquid water in the atmosphere of these planets. So this is by observing the scattering due to a rainbow. So the rainbow is produced by internal scattering in the droplets of the liquid in the atmosphere, okay? And there is preferred angle for each liquid with different refractive indices and the different sizes of the droplets. So that sort of measurement is actually very difficult, well, not possible at this stage, I should say, to do for exoplanets. It has been done, though, for Venus a long time ago in 1974 by Hansen and Hovenier. And what they did, they observed polarization across the whole orbital phase of Venus. And they found that there is this strong peak in the polarization, which is pretty much from the scattering of rainbow. And this is what they found. The angle of the scattering corresponded to actually the liquid being sulfuric acid mixed with water. So that was before we actually sent the probe to Venus and found out that this is what it is. Venus actually has sulfuric acid clouds. And that there's also this Rayleigh scattering peak and some backscattering peak as well. So, well, can we do it for exoplanets? It would be nice, but not at this stage, unfortunately. Another possibility of looking at really liquid water on the surface, as I mentioned, is this observation of the specular reflection. And this is the glint, which here you could see from International Space Station, from the glint from the ocean on the Earth. Unfortunately, this is only the Earth, not exoplanet. Now, so glint is highly polarized. The models presented for it suggest that the polarization can be, for Earth geography, can be as high as 30%. But unfortunately, the amount of light from the whole planet is not that high, because this occurs at this effect occurs at the sort of shallow angles. So this is only when the planet is in the sort of crescent phase. So this is actually here the example of glint observed on Titan, and that was done by Cassini. So Cassini actually seen the specular reflection from the lake on Titan, and we think these are hydrocarbon lakes on that moon. So this is just to show you that the glint is actually polarized, so it has no wind. You can see quite strong polarization. These are two different modes of polarization together. Wind and any conditions like clouds and so on will obviously dampen this effect. So again,
if I take any liquid and make it smooth, will it have the same amount of reflection?
I think yeah. So that, yeah, so this depends, I suppose. It depends probably on the composition of the liquid as well, because this is a dielectric. Yeah, that Penny is actually waving. Yeah. So I believe, there would be probably some difference in how much.
So that image of Titan you showed, reflection of hydrocarbon lake, would that have been brighter or less bright for water?
That's a good question. I can't answer that. I don't know what it is for the hydrocarbons. So probably someone modeled it before. So that would be interesting thing to see. Well, what we see here, this is not a polarized light. Yeah, so this is just a total flux. Yeah.
If I had to think water or polarizing,
But this is not polarized. It's just
No, this is just a reflection. Yeah. So, okay, so, right. So if we want to really observe all these effects, what are the advantages and challenges? Okay, so as we already seen in many talks here, planets are many orders of magnitude fainter than stars. And this is a bit of a problem. Now, the other problem is that to compensate for this, we try to observe in infrared where this ratio is smaller. But in case of polarized emission, well, unfortunately, a thermal emission which dominates the infrared emission is unpolarized. So we really are sort of forced to stay in the visible light. And but there are some good news. There is some good news. Well, it turns out that when we're looking at the starlight, direct starlight, when we integrate it over the stellar disk, which we usually, that's how we see the star, that is usually unpolarized. And I have to sort of mention here that that's not always the truth, that's for the stars which are similar to our own sun. For giants and other sort of strange stars, actually they can have polarization, appreciable polarization, and one of our member of our team, Daniel Cotton, is actually investigating these effects. Now, so when we see unpolarized star and we don't resolve the planet, and if we see some polarization, we can assume pretty safely that that polarization comes actually from the planet. So what we do, we can use something called aperture polarimetry. So, the best would be just to image the planet, but we don't do it because it's too hard. The ratio is too hard. So we observe the whole system, and we assume that if we've got the polarized light, and it can be polarized up to 50% due to Rayleigh scattering, that's fine. But the problem is that, that the actually percentage polarization which we see is not that high, because the starlight which is reflected is actually quite a small fraction of the stellar light. So really we're looking at the 10 to minus 5, so parts per million of polarized light. So you've got 1 or 2 polarized photons together with a million of them. So you really need very, very sort of bright objects, and you need to collect a lot of light to actually be able to detect this polarized emission. So as I mentioned here, or written here, this maximum polarization will depend on the size of the planet and its distance from the star. Okay, so let's recap quickly. So the degree of polarization depends, which we can see, depends on the composition and structure of the planet's atmosphere, the reflection properties of the planet's surface, the wavelength of the light which we observe, and also on the planetary phase angle. And as we already discussed this, we've got here new phase, and then the angle about 74, which corresponds to that glint reflection, and then around 90 degrees maximum polarization due to Rayleigh, And then close to like 40 degrees from 180 full phase, we've got rainbow, possible rainbow feature, which we could try to observe. So the good news is the polarization is a differential measurement, and we can actually, we don't need to go to, space. We can achieve the part per million precision from the ground, but we are really starving for photons, so we have to have big telescopes. Now, high sensitivity polarimetry is required, as I already sort of try to allude to. So these are the first models for hot Jupiters, which indicate that yes, you would have to have sensitive polarimetry to measure 5 or 50 parts per million, and this leaves us only with the hot Jupiter polarization at hot Jupiter detections. Now we've got more sophisticated models where we can put clouds into these models as well, and they are actually informed by the measurements of the transmission spectra. And this is for one of these hot Jupiters, showing transmission spectrum showing that there's a lot of absorption in the atmosphere, and this is modeled with the cloud particles which match the transit measurements. So we also showing that the highest polarization would be for that sort of clouds would be of the order, this is a polarization here, this is total flux, so it'd be of the order of 50%, but actual observed polarization when we sort of divide it by the flux from the star, it's only about 20 parts per million. So, well, our models are that sophisticated that we actually can measure polarization at the surface of the planet at different phases. So this is Jeremy's Bailey's sort of movie. He sort of shows here the different phase angles and what the polarization due to Rayleigh scattering looks like in it, and what is actually observable fraction of polarized light. I won't be sort of showing the whole lot of it, but you can see the polarization reaches the peak around 90 degrees, as we expected. Okay, so let's go quickly through observations. So we built this high precision polarimetric instrument called HIPI, and this is still the world's most sensitive stellar polarimeter, which gives us 4 parts per million fractional polarization, compared with typical polarimeters, which can do 0.1% or so. This is our team. So you're probably familiar with some of these people. These are people from UK, and I never met them in person. Somehow we only talk on the, yeah. Okay, so what is HIPI? This is a dual channel aperture polarimeter. So it has a ferroelectric liquid crystal modulator, which is very important for its design, and very sensitive detectors. Now, it also has lightweight 3D printed components, so that makes it very light, and we can use it as a visiting instrument. So, what it's measured here? So this FLC crystal acts as a retarder, so it's changing rapidly the sense of polarimetry, polarization, and then the beam of light is split into 2 different polarizations. So here we can sort of talk about it as in terms of Stokes parameters. So you've got 2 different polarization, which gives you I Stokes, which is the total flux, and Q and U are differences between these 2 polarization sort of polarized fluxes. Now, the liquid, FLC modulator actually changes polarization 500 times per second, which really allows us to minimize systematic due to seeing in the atmosphere. And then we use as detectors these ultra alkali photomultipliers, which are sensitive, highly sensitive, actually 43% quantum efficiency in the blue light. And this is where we actually expect the highest signal from the Rayleigh scattering. So, yep, almost there. So we've got 3-stage modulation as well. So we can rotate. So we do this modulation with this FLC. We also can rotate the part of the instrument with Wolfson crystals. So that allows us to subtract some instrumental problems. And the 3rd stage, when we actually can rotate the telescope position angle. Okay, so the data, these are our measurements of this Q over I and U over I for the one called Jupiter, which I showed you the model for before. The model is consistent with our measurements, or our measurements sort of indicate that we see the maximum 20 parts per million of the polarization due to Rayleigh scattering. Now that's in disagreement with the previous measurement by Berduguina, who et al., who found many more times higher polarization, and probably the polarization measurement was contaminated by the polarization of the dust on the Earth as well. So maybe they didn't subtract that. And our data is actually confirmed, but another group, Viktorovich et al., who got almost as sensitive polarimeter as ours, and they're doing pretty good job with it too. Okay, and so quickly, this is our sample at AAT. Not many objects, unfortunately. So we really need more photons. If we had the whole sky available with that sort of telescope, still the sample would be very small. So what we're trying to do, we're trying to snatch the 8-meter telescope and put another polarimeter on it, and this is HIPI 2, which Jeremy Bailey's designed and actually single-handedly built already, and it's going on that telescope. So yeah, these are the quick features of it. So we've got again lightweight instrument which we can carry around, and we have to operate it remotely because Gemini operations of the telescope are actually remote. So we actually can run this little all the filter wheels and aperture rotators and so on from the website, which is nice. Okay, and that will give us quite a few more objects which we can observe. I didn't put names on it at all, but this is still not that good because this is still radius of the higher than the radius of the Jupiter, and catching up only one super Earth type of object. So that's what we need. We need Great Magellan Telescope, and so this one's got 25 meter segmented mirror and so on, and it's being constructed now. Maybe we will be lucky enough to put our polarimeter there. That would really change the parameter space for us, so we could really start looking at the planets which are in the range of the Neptunes and super Earths, and looking actually at the cooler atmospheres, the planets which are further away from the parent star. So I guess I'm finishing here. So with the conclusions, which tell you that polarimetry detections of scattered light are currently feasible, and we're doing this, but we still would like larger telescopes, wouldn't, I suppose. And we're actually examining this intrinsic stellar polarization, which is a nuisance for us, and could produce noise. And as for detection of liquid water, well, I just leave it with this, that you know, this is for new generation of telescopes and new generation of students. So you guys are going to probably do it. Yeah, that's it. Thanks.